Hey everybody, this is Alex, speaking from COVID-induced home confinement. In case you're going to hear noise in the background, that's just my family doing stuff. And in today's podcast episode, we are going to talk about countdown latches. I heard that if you know how to implement a countdown latch, this increases your chances of being hired. I'm kidding, of course. But knowing how to implement a countdown latch can be a useful exercise, and it's a useful concurrency primitive to have in your toolbox. Note that today we are not going to use Monix, we are not going to use cat's effect, we are not going to use software transactional memory, and it's debatable if software transactional memory would bring any value to the table for this particular task. But today we are going to use just the standard library because it's not about functional programming, it's about concurrency on top of the JVM. But if you want to suspend those side effects in IO or other effect data types, be my guest. The same techniques can be used. So let's get started and have some fun. First, let's define what a countdown latch is. The countdown latch is a concurrency primitive that gets initialized with a count, an internal counter, and it provides two operations: the countdown, which decrements that counter towards 0, and when it reaches 0, all the consumers that are awaiting via this other method will get a signal to proceed processing. So the countdown latch is a way to wait on other threads to finish whatever it is that they are doing in order to proceed with the processing from some main thread somewhere. And let's do a stupid sample to illustrate how we can work with a countdown latch. Let's say that we want to initialize a bunch of threads. We are going to work with 4 threads. And we need a thread pool. We could initialize those threads directly, but let's not do that for now. So going in a loop and starting some threads via the execute method of our thread pool. Let's also use the blocking context like the good Scala citizens that we are to instruct the underlying thread pool that we are doing something blocking, because we will. And let's say that we want to test. So the countdown latch is awesome for testing concurrency abstractions. And what we want to do is create a bunch of threads that trigger some effect, mutate some shared state, and we want to know if our algorithm is correct by creating concurrency, by having multiple threads contend on the same shared resource to see what happens. So first of all, we are going to start our threads, and then we are going to wait for our threads to have started before proceeding to do something else. So we will have to first have something like consumers started, as a countdown latch, and we are going to initialize as equal to the number of threads that we are working with. To decrement this count inside our threads, so our threads, when one of these threads starts, we are going to trigger its countdown method. And here in our main thread, we can simply await on it. We can wait for forever, or we could specify a timeout, in which case the method can quit early. But we are going to wait forever. That's fine for our purposes here. And one other thing we can do is to wait for the signal of the main thread to proceed, to increase like precision there. So we could say consumers main thread proceed, and this is going to be initialized with an initial count of 1 because it's a signal that's going to be transmitted by our main thread countdown. So here we can say main thread proceed. Await. This is because we want to ensure that our main thread is ready as well. It's not necessarily needed here for the purposes of this sample, but it can illustrate how this kind of orchestration can work, you know, to ensure that we can ensure here that all of the threads have started. We can ensure that the main thread is ready before proceeding, you know, to maybe visualize the results or whatever. And here let's have some shared state expressed as a variable, and we are going to mutate that shared state. It is unsafe, and we want to test this unsafety. I mean, we know here that it's unsafe, but in other cases the algorithms might get complicated, so information via unit test that everything is fine. So we are incrementing our shared state. This would be the workload, and then we need to signal to the main thread that everything was processed. So all of the threads have processed and have basically done whatever they were supposed to do. So we'll need another countdown latch. Let's name it consumers finished countdown latch with thread count, and we are going to do our countdown here. So consumer finished countdown, and then here we are going to wait for all the consumers to finish whatever it is that they are doing, and afterwards we need to aggregate the results somehow. And by the way, we are trying to simulate a concurrency problem here, and the problem with concurrency algorithms is that the effects can be really subtle, and they might not happen, so they may happen non-deterministically, and they could be really rare. So with just one execution we might not see the effect that we are looking for. So in such tests, it's a good idea to execute the test multiple times. So we are going to do a for loop. And now maybe we can think about aggregating our results. Let's do a map, and in that map we want to aggregate how many times we've seen a particular result. We want to count the results that we are getting. You'll see why in a minute. So given that we have a shared state result, we want to increment its occurrence in our map, and afterwards we can say done, and print our results. we can now try to execute this code. 1 million iterations, it's going to take a while, but I needed to ensure that we kind of get the effect that we were expecting. This is obviously wrong what we are doing here, but concurrency problems are really subtle, and it takes a while to it can take a while to see corrupt data because we've lost updates on the way due to concurrency. So this is why I've started with straight up 1 million iterations. In an actual unit test, we would work with fewer iterations than this, like 1000 or something like that, and hope that eventually we will get the desired outcome. I mean, not desired, the undesirable outcome in a test, maybe in continuous integration and so on. But yeah, it takes a while. So as you can see here, oh, did we just log starting repeatedly? Okay, yeah, that's not good. Anyway, so we've seen the result for like 999,975 times, and we've seen updates being dropped like 25 times out of those 1 million iterations. But yes, we could reproduce the fault in our code. We can now clearly see that this shared state is wrongly accessed and updated here. And we needed the countdown latch because we wanted to maximize the success rate of our test, because creating threads may be expensive. Maybe the thread pool is busy with something else. So, you know, creating one thread and executing it might happen really fast, and then another thread created and executing its workload again might happen really fast, and the thread creation might end up being actually sequential, being an issue of timing. So we want to ensure, to maximize the success rate of our test, we want to ensure that all the threads are being started before proceeding doing something else. And then at the end, we want to ensure that all of the threads have finished before aggregating the results and seeing what happened. So we can see like this dual use of the countdown latch here. We first await for the threads to have started, and then we await those threads to have finished their processing before aggregating the results. So we can see that this would be like a really useful concurrency primitive to have at times, especially in testing. So I use the countdown latch in testing all the time. Now, the countdown latch in Java standard library is pretty useful on its own. We don't need to re-implement it, even though it blocks threads, but sometimes blocking threads is precisely what you want. But let's say in order to provide some value here, we might want a countdown latch that works asynchronously, that doesn't block any threads, so that it works with future. So let's describe such a class. Async countdown latch, we would have an initial count. By the way, I may do mistakes while implementing this class because I don't have like a written script or anything. Let's just work together on this. Now, straight from the get-go, I'm not going to use Java's intrinsic blocks, meaning those synchronized blocks for synchronization, even though that's a perfectly valid way to deal with concurrency on top of the JVM, and sometimes it's maybe the best choice. But what I'm going to use my favorite way of dealing with concurrency on the JVM, because it's cheap and it's easy and it works well with immutable data structures. So my favorite way of dealing with concurrency of the JVM is the atomic reference. So we are going to have an atomic reference here that's going to keep the shared state. And here we need to specify some state. Let's do that in our companion object, because in the companion object is the perfect place to, you know, describe whatever internal utilities we may need. The state must be an immutable data structure if we are going to use an atomic reference. So we are going to have again our counter and we are going to have a bunch of tasks to execute. We can simply use a list, it doesn't really matter, but these tasks are going to be promises to complete whenever the countdown reaches 0. And I got ahead of myself here. We should have started with the definitions with the signatures. We need a countdown that can return unit, that's fine. But we'll need an await that returns a future of unit. So instead of returning unit, it's going to return a future of unit, such that we can wait for the countdown to reach 0 asynchronously without blocking any threads. This is cool right now. So here we can like import async CountDownLatch state, and here we can simply initialize the state to an initial count and an empty list. And now we are good to go. So we have our shared mutable state, we have our signatures that we need to implement. Let's get started. Now, the way to work with an atomic reference is to describe a loop. So first we need to fetch the current state using get. We need to capture this reference because we'll need it later, so we need a name for it, and I prefer to use current. But we can deconstruct it to get the values inside the tasks. Now, what should we do? Well, if the count is greater than 0, then we need to issue an update incrementing it. And then the way this will work is to go into a compare and set loop. So we try a compare and set operation, and the compare and set wants the current reference that's stored there and an update. And in case this fails, we retry the countdown. Now, compare and set basically returns a Boolean value. It returns a true value in case the update succeeded, or it returns a false value in case there was a concurrent update and the update did not succeed. So in other words, concurrency happened, so we need to retry the update. So it's like in a database where the transaction failed and it needs to be retried. Same principle holds here. Now, in case our update succeeded, then we can like do something else. In this case, I don't think there's anything else that we need to worry about. Do we need? Oh, no. In case of else, oh my god, yeah. In case of in case the count Okay, in case the count reached 0, else if update count reached 0, now we are talking. So in this case, we need to trigger the tasks, the notifications. We have got listeners being subscribed to our notifications. We should trigger them all. So yeah, try success with a value of unit. By the way, here we are using multiple promises. We are using a list of promises, but a promise allows for subscribing multiple listeners to it. So why did we use multiple promises? Well, we may need to get rid of some of those promises, and I'll show you why in a minute after we implement await. So in this case, working with a bunch of promises is a better idea than working with just one promise. But let's implement await too. So it's the same pattern with this compare set. We first fetch the current state, and we try, well, we need to see if the count has reached 0 first. So if the count has reached 0, then there's nothing to wait for, so we return an already completed promise. Otherwise, if the count is different from 0, we create a new promise. We create a new update value. And we try to update our state. Compare and set current and update. If that's false, then concurrency happened, so we need to retry. Otherwise, do we need to do anything else? Yes, we need to do. We need to return our created future. By the way, when doing these pattern matches, it's probably a good idea to test for nullability too. Now, normally we shouldn't work with null, but this, let's say, will be a low-level implementation, because it is. We are working directly with atomic references. This is a concurrency primitive that should be well encapsulated, so it's perfectly possible to shove that null value in this atomic reference to maybe get rid of the junk such that garbage collection can collect it or do whatever it is that it does. So we when doing the countdown here, we might want to like do something like state lazy set null for garbage collection purposes, and then we can say case null, like ignore. This is really unsafe. I hate nullability, but when you know what you're doing and in case you want to like do something really low level, you can simply do this, right? So just, this is like word of mouth typing. We can't see null, but it's there, and we've just introduced it here. Now maybe in Scala 3 we'll be able to use untagged union types for expressing or null, which would be like so awesome, but right now we can't, so we are just going to assume that it's there. And again, this is not high-level code. In high-level code, never work with null, but this is a low-level concurrency primitive, so with a low-level implementation, a concurrency primitive with a low-level implementation. So it's perfectly fine. Now I believe that at this point our job is done. I hope that I haven't introduced any bugs here. What happens if count is 0 here? Well, we don't care. If count is we don't care, else. Okay, so this looks fine. But in our CountDownLatch definition here, we also had this overload of await that accepted a timeout parameter. And this would be a good idea because future is not cancelable. I mean, if future were cancelable, we could have described an external timeout that does the right thing. Timeout as a reusable function for futures, but we can't do that unless you use cancelable future from Monix, which supports that, or unless you used like IO from Cat's Effect or task from Monix, which are cancelable. But we don't use that here, we use future. So it might be a good idea to specify an explicit timeout, taking as parameter so a timeout taken as a parameter of this function that we need to use somehow. But now we need a way to trigger such timeouts. So in order to trigger a timeout, we would need a scheduler, which is a thread pool with an executor with scheduling capabilities. Now we could take it as a parameter here, and that's fine. But for the purposes of this exercise, we are going to initialize it internally and manage it internally. It's debatable on whether you should do this at home or not. So we could see new scheduled, new single thread scheduler, new single thread scheduled executor. Executors is like this class having static functions from Java util concurrent, and it allows you to quickly create thread pools. Now when creating a thread pool, it's a good idea to give it a custom thread factory in which we specify how threads should be created and their properties. So for example, I prefer my threads to be daemon threads in this case because I don't want them to block main. I'd rather have an explicit name for these threads such that I can recognize them from whenever doing profiling. So we could say, I think, CountDownLatch, and then we could have, I don't know, hash code maybe, something like that. That's fine. Maybe we could also specify what happens when this thread pool catches an uncaught exception. So we could have like also have like set uncaught exception handler, but we are not going to do that in this case. The scheduler is going to be responsible only for scheduling, and the tasks that we are going to shove in it are not going to be blocking or are not going to be able to trigger any exceptions, hopefully. So one other thing that we need to describe now that we have a scheduler, let's describe a generic helper here. So for our ability to specify a timeout with timeout, and this function is going to take a promise and timeout as a duration, finite duration. At this point it should be a known quantity. Maybe install timeout, yeah, because we are going to do side effects like a boss here. Okay, so first we need a timeout task. That's going to be a runnable, because that's what these executors are using Scala syntax for lambdas. And first of all, we need to try completing our future with a timeout exception, because I mean that's the effect we are looking for. Async CountDownLatch, await, and we can give it our timeout for debugging purposes. Now there is one issue. Whenever we timeout like this, we need to this is a race condition between two tasks. It could have been easily described with cat's effect or the Monix task, but we are not there. We are not using those libraries. Right now we are implementing our own thing. So we need to take care of memory leaks. What does this mean? If our timeout task wins, we need to we need to do some cleanup of our state. So we need to remove this promise from the list of tasks to be completed. First of all, so this is the list in our state here. Removing one promise from it is an O(n) operation, so we might want to use maybe a set here, because iterating over it with a plain iterator doesn't cost us that much. A set would be better, I think, in this particular case, maybe. Always benchmark, of course. So let's here we need to do the cleanup. Again, this is not scripted. I don't have the code ready. I'm developing it with you right now. Here we need to like go into a loop, so remove promise from our same pattern, state get match case we could say update copy tasks, and then so we keep retrying until we succeed or until we can no longer proceed. Same pattern as everywhere else. So we are removing our promise, taking care of the leak here, and we are doing we are trying to complete our promise with a timeout exception here, but there's also a leak in the other direction, a possible leak in the other direction. So whenever our source promise gets completed with success, we need to remove our timeout task from the scheduler. So first let's install our timeout task in the scheduler. We'll get a cancel token back. Cool. And this is the cancel token that we need removed. So in case we can install a non-complete on our future. We can install a non-complete that does nothing else but to cancel our token. Let's take care of the duplication here. So in case of case success, or case failure, should we, like, would there be a better way to express this? Is, can't we just query this? So is success or error or fail? Try is so limited. Why is it so limited? Oh, fuck it. Fans of so the fans of Scala's pattern matching and exhaustiveness checking are having heart attack right now. So if trigger, then cancel token cancel. But by the way, this code could be type checked if we had flow based type checking. This is basically something like this is basically possible in TypeScript to have it correctly type checked. Not in Scala, not yet anyway. So this get is a partial function here, and you know, that's fine because try is well established. Well, we might have one problem here. In order to install a non-complete handler, we may need an execution context too. Okay, let's do that. We are complicating our implementation, but fine. We are working with future after all. An execution context was inevitable. Now we have our install timeout utility here that is useful for installing a timeout on promises. We take care of the memory leak in case our primary task succeeds, and we take care of the memory leak in case our timeout task succeeds instead, so by removing the promise. So in both cases we are covered. Now, when doing the timeout, are there any changes here? Well, sure, we need to do stuff for garbage collecting purposes. Maybe now that we have an explicit scheduler in our implementation, it's not such a bad idea to implement this closable interface from Java. This is actually terrible compared with the resource abstraction from Cat's effect. So resource is a great data type. You should always prefer it over auto-closable, but this is what the Java standard library wants us to use, and that's what we are going to use, because why not? We are stateful anyway. In our close, we can say state lazy set null for GC purposes, and scheduler shutdown. Okay, now here, instead of simply setting this to null, we can just call close, and that's it. In case our update, so in case our countdown goes to 0, we shut down our scheduler too, right away. Now await gets more complicated. First of all, now we add a promise to our tasks via the set interface. In case we have a timeout as a duration, a finite duration, in case it's a finite duration, we say install timeout, and we give it our promise and our finite duration. Otherwise, you know, do nothing. Did we succeed in implementing an async countdown latch? This is pretty cool, and I think we did. Unused, yeah, let's take care of this. I hate unused. Yeah, sure. Let's declare this as tailrec to have the compiler protect us against accidental errors. Now let's describe our logic here using this new countdown, this new async countdown latch. Well, it's not exactly the same, but you know, consumers started. How should we describe this? Yeah, so let's change our logic based on our concurrent asynchronous countdown latch. It doesn't necessarily make the same sense, by the way. I mean, this is going to be totally useless, but you can like imagine like a real world use case that actually makes sense and will make your coworkers happy. So what we have for threads instead? Well, we have future stuff. So we are going to like flat map on a future unit. We are then going to say consumer started countdown. Like this. We are going to then wait on the main thread proceed await with a duration, infinite duration. Okay, let's do infinite. We are going to then mutate our shared state, and then we are going to signal that we have, oh, wait, it's fine if we do this. Yeah, this is such an awkward piece of logic, I mean, but anyway. Now here we can do duration infinite, countdown, duration infinite, but this needs to be awaited, so let's do a for comprehension here too, because that's how we roll in Scala. You're not a Scala developer unless you do weird things with for comprehensions. Yeah. And we are going to block our current thread because why not? This needs a timeout too. Let's do less iterations because this is not healthy for our self-esteem. That's my parrot you're hearing in the background. I have such an annoying parrot. I love him, but he's so noisy. Oh wow, so it takes a while. Okay, we just 100 iterations, we might have... Oh shit. What did we do here? Wait. No. Yeah, so yeah, we should have done something like yield sequence no, actually it should have been okay, because you know future is side effecting. Let's do just 4 iterations. Maybe it's like really slow. Go. Iterations. Okay, we are being blocked forever because our logic is shit. But that's fine, our hope is still up. Let's see if we can spot the error. So, state get, getting the current state. In case the count is greater than 0, we update by, oh shit, we are increasing the count instead of decreasing. Okay, that's bad. Stop. Delete, garbage collect, everything. Okay, yeah, let's try again. Go, come on. Yes, that was it. Oh my god. I have such great debugging skills. Whenever I sum up numbers instead of subtracting them, I just feel it. Okay, so here is the concurrency issue. We can detect it in just 1000 iterations. And yeah, notice how here we basically, instead of waiting on a sequence, you know, waiting for some futures to be complete can be done just with future.sequence or something, but maybe this is still useful in certain scenarios. I don't know. It could be, but yeah, it works. Our class, our implementation here works. Let's also do let's wait here just for 1 millisecond. Okay, this should eventually trigger a timeout. Let's see. Rejected? What? Is this like reusing? Is this, I don't know, reusing instances or something? I don't know how this worksheet works, but it seems like it's reusing instances. So well, if we are not going to like do the await here like this, will this now work? Yes. Okay, we are doing something wrong. We are doing something wrong. What are we doing wrong? So we are installing the timeout. Let's do like a, okay. We have a race condition. We have a race condition. What race condition are we having? So, okay, here, try. This is what happens when you like. So we get a rejected execution exception because our scheduler was shut down, maybe because the logic has finished and rejection happens, something happens asynchronously anyway. In that case, no. Try failure X directly. So yeah. Oh, this is a catch. So what I did before was that I was saying here only wait for one millisecond. Now it works. Yeah. Here it is. Nice. Let's say catch. In case we have a timeout exception, we are going to say that the results is equivalent to 0. This one should have been get or else. Okay. Now, go. Yeah. Let's do more iterations. Let's do 10,000. Are we not getting a 0? Interesting. Everything works. Something happened. I don't know what. I'm still unsure about what would make this trigger a rejected execution exception. Let's use my awesome debugging skills here. Not completed. Maybe there's something wrong with how I'm doing the shutdown. Could I do a shutdown now? Oh, maybe does this shutdown trigger some exception? No. But okay, so schedule could. At what line? What line are you doing here? 26. Line 26? Uh-huh. Yeah, I believe this is natural. So basically there's a race condition between installing a promise. So we add a promise to our state, but before returning that promise to our caller, the countdown reached the 0 and the task was already completed. And in that case, the task may have already been completed, and in that case we should probably do nothing, because we risk race condition, another race condition. In case the scheduler was in case the scheduler was already shut down, it means the countdown went to 0 already, and it means that all the promises are in the process of being completed, so we should do nothing there. Yeah, race conditions are fun. Okay. So now it works and it's fine. Yeah. So there you have it, folks. One mention here, I ended up doing low-level resource processing. This is unneeded if you would work with data types that already implement this timeout concept for you. So what's difficult about implementing your own timeouts like this is the resource handling. Whenever you install a timeout in an executor, you have to also prematurely cancel that timeout in case your primary task has completed on time, and vice versa. Whenever you trigger a timeout task in your scheduler, you also have to ensure that your task that is running is cancelled. In this case, the cancellation means to pull it out from your internal queue of callbacks to be called whenever the countdown reaches 0. You can basically bypass this by reusing, for example, stuff from Monix. So Monix has a cancelable future which you could use. For example, cancellation being, for example, this ability to pull that task out from your internal queue. You could specify, you could build like a cancelable feature that on cancellation removes that promise from the internal queue. And this, I believe, also has, does it have a timeout straight? No. I believe there's another future utils, maybe. Yes, there's another future utils that specifies a timeout operation, and this actually works with cancelable future, and it uses cancelable future. On plain futures, it can create a memory leak, but otherwise, yeah, it can work with cancelable future too. Or you could use task from Monix. I mean task. This one has a timeout too, so it would be like easy. Timeout. Yeah, here it is. So this has a timeout operation specified on task itself, which creates that race condition and everything is taken care of, and the task cancellation could again pull that call back out of that internal queue, and ditto for the IO monad specified in cat's effect, and so on. So here we went low level, and you've seen like what it takes to basically race 2 tasks to completion and cancel one of them. But it's all doable. I mean, I just did it in what, half an hour to an hour? Yeah. But of course I knew what I was doing, but you can do that too. So go through this exercise. It's a really educative one. Like, try to build what I did here on your own. And a blog article will accompany this video for you to copy paste the code, which I don't necessarily recommend using in production because it's not tested yet. I mean, like, don't copy paste this into your production code without further testing it, or, you know, reusing what's already available out there, like the CountDownLatch from Java's standard library, because that's probably what you need and not this asynchronous version. But you know, this can be useful, and it's a useful exercise for you, and you can use the techniques that I described here. So I hope you found this useful, and yeah, See you next time. Cheers.